Welcome to the Deep Dive. Today, we're going to be diving into some pretty heady stuff. Isaac Newton's views on space, time, and motion.
Oh, yeah.
Buckle up, because we're about to time travel back to the 17th century. Grapple with ideas that shook the very foundations of science and philosophy.
Right.
And explore why they still matter today.
Yeah, it's really fascinating how these concepts, debated centuries ago, continue to shape our understanding of the universe.
Yeah.
Especially for a philosopher like you,
Oh,
who's
yeah.
constantly questioning the nature of reality.
And for this deep dive, we have excerpts from the Stanford Encyclopedia of Philosophy's article on Newton's views on space, time, and motion.
Yes.
We're going to unpack how Newton's ideas revolutionized our understanding of the cosmos and why they sparked fierce debates with thinkers like
Oh, yeah.
Leibniz, Berkeley, and Descartes.
Big names.
Yeah, huge names.
To grasp the heart of the matter, though, I think we need to start with Newton's core concepts.
Yeah.
Absolute space and absolute time. He saw these as separate, unchanging, and independent of anything physical.
Okay.
So imagine a cosmic stage upon which the entire universe unfolds.
Okay.
That's absolute space
Gotcha.
and absolute time.
Yeah.
It's like a universal clock that ticks on, relentlessly uninfluenced by anything happening within the universe.
So even if the universe were completely empty at this stage and this clock would still exist,
Yes,
that's a pretty bold claim.
it is.
Yeah.
It is, and it goes against the grain of what many thinkers believed at the time. See, even in ancient Greece, there was this debate about the void.
Okay.
Aristotle argued for a universe completely full of matter, a plenum,
Right.
where there's no such thing as empty space.
Yeah.
On the other hand, the atomists believed in tiny indivisible particles with empty space between them.
Okay, so imagine two atoms hurtling through the universe.
Right.
For Aristotle, there's always some kind of matter between them pushing them along.
Yeah.
But for the atomists, they're moving through genuine emptiness. That's a huge difference.
It is a huge difference. It's not just theoretical.
Yeah.
It has massive implications for how we understand motion forces and even God's presence in the universe.
Oh, wow.
Thinkers like Walter Charlton in the 17th century argued that this void existed even before God created the world.
Okay.
Imagine that space existing before anything else.
That's mind-blowing.
Yeah.
And this is where Newton comes in with his radical idea of true motion.
Yes.
He's saying, hold on, a body's true motion is its movement through this absolute space.
Yes.
This cosmic stage.
This cosmic stage.
It's not just about how it's moving relative to other objects.
right.
It's about its absolute change in position on this grand, invisible grid.
You've got it.
Okay.
And for Newton, this framework was essential to make sense of the universe and the laws that govern it.
So now I'm thinking, if we can't see this absolute space, how can we even know that it's there?
Right.
It's not like we can reach out and touch it.
That's the million-dollar question.
Yeah.
And that's precisely what Newton sets out to do in his famous Scholium, a philosophical preface to his groundbreaking work, the Principia.
Yeah.
He presents 5 arguments in defense of absolute space and motion,
Okay.
each one more intricate than the last.
Okay.
And this, my friend, is where things get really interesting.
Okay. I'm ready to dive into these arguments. What's the first one all about?
All right, so Newton starts by tackling the concept of true rest.
Okay.
He argues that if two bodies are truly at rest, they're at rest relative to one another.
Right.
But here's the catch. We can never know the position of every single body in the universe.
Okay.
There's always a chance that something somewhere is moving.
So if absolute rest is based on knowing the state of the entire universe,
Yes.
and that's impossible, does that mean absolute rest is a meaningless concept?
That's a very sharp observation.
It's a bit like chasing a phantom, isn't it?
It is, and it leads us right into Newton's second argument, which focuses on the relationship between a part and the whole.
Okay.
Let's say you're on a train, peacefully reading a book.
Okay.
You're at rest relative to the train, but the train itself is moving, hurtling through space.
So even if you feel like you're perfectly still, you're actually moving along with the train.
Exactly.
And ultimately moving through this absolute space that Newton is so adamant about.
Precisely. True motion can't just be about your immediate surroundings. It has to encompass a larger context, culminating in this ultimate unmoving frame of reference,
Yep.
absolute space.
Gotcha.
And this brings us to his third argument, which gets even more mind-bending.
Okay. I'm intrigued. Lay it on me.
Newton argues that a body's total movement is the sum of all its motions relative to increasingly larger moving places.
Okay.
Imagine it like those Russian nesting dolls,
Right.
but with motion instead of dolls.
Gotcha.
To get the complete picture to understand true motion, you need a final unmoving reference point.
Okay.
And that, he claims, is absolute space.
So each layer of motion builds upon the one before it,
Yes.
but you need a solid foundation to make sense of it all.
Yes.
It's like building a tower without a stable base. The whole thing collapses.
That's a great analogy.
Yeah.
And with these first three arguments, Newton lays the groundwork for his final two, which focus on the causes and effects of motion.
Okay.
But before we get to those, let's pause here for a moment.
Right.
For a philosopher like you, does the idea of absolute space hold up so far? Or are you already sensing some cracks in Newton's grand scheme?
Honestly, it's both fascinating and frustrating.
Okay.
On one hand, it's a compelling way to try to make sense of motion.
Yeah.
But on the other hand, if you can't observe this absolute space,
Yeah.
how can you truly know it's there?
Right.
It feels like a leap of faith,
Yeah.
almost like a philosophical assumption
Yeah.
rather than a scientific fact.
You've hit on a key point of contention, and it's one that philosophers and scientists have been grappling with for centuries. So let's unpack those last two arguments, shall we?
Okay.
I have a feeling they'll spark even more philosophical debate.
Lead the way. I'm eager to see where this all leads.
All right, so we've explored the first three of Newton's arguments for absolute space, and I'm already feeling like my brain is doing backflips.
Oh, yeah.
Where do those last two arguments take us?
Well, they delve into the nitty-gritty of how motion works, its causes and effects.
Okay.
Newton's fourth argument centers around the idea of force.
Okay.
He proposes that applying force changes a body's true motion through absolute space,
Okay.
even if its motion relative to other objects remains the same.
Can you give me an example of what you mean?
Sure.
It's hard to picture how force can be linked to something invisible, like absolute space.
Yeah, so picture this.
Yeah.
You have a group of objects floating together in space,
Right.
perfectly still relative to each other.
All right.
Now imagine a gentle but constant force pushing on them equally.
Okay.
Their positions relative to each other wouldn't change.
Duh.
They'd still be clustered together.
Right.
But their true motion through absolute space would be altered.
Okay.
They'd be moving as one unit across that cosmic stage. Ah, I see. So even though their relative positions stay the same, their overall movement through this invisible absolute space has changed thanks to that force.
Exactly.
Force becomes a kind of marker pointing to movement beyond what we can directly observe.
Exactly. Force acts as a bridge between the visible and the invisible, the relative and the absolute.
Okay.
And this brings us to Newton's fifth and perhaps most famous argument,
Okay.
the one involving the rotating bucket.
Yes.
This is where things get really wild, especially for a philosopher concerned with how we perceive reality.
Okay, I've heard whispers of this infamous bucket. Bring on the thought experiment.
All right, so imagine a bucket filled with water hanging from a rope.
Okay.
At first, both the bucket and the water are still.
Gotcha.
Then you twist the rope, setting the bucket spinning.
Okay.
Initially, the water remains flat,
Okay.
but as the bucket continues to spin, the water starts to rotate, with it eventually forming a concave surface.
I can picture it, that swirling vortex in the bucket as the water catches up to the bucket spin.
Yeah.
But how does this prove anything about absolute space?
Here's the key insight. If all motion were truly relative, then the only thing that should matter is the relative motion between the water and the bucket.
Okay.
When they're both still no motion, no force.
Oh,
When the bucket spins and the water is still, we have relative motion.
right.
But once the water catches up and they're spinning together, they're once again at relative rest.
Right.
Right.
Yeah, that makes sense. If it's only about the relationship between the water and the bucket, the forces should disappear once they're both rotating together.
Exactly.
But that's not what happens, is it?
Exactly. The water surface remains concave even when it's no longer moving relative to the bucket. This suggests there's a force acting on the water, pushing it outwards, even though it's at relative rest with the bucket.
Okay.
This force, centrifugal force, is evidence that the water is still in motion, but motion relative to something else, something beyond the immediate relationship with the bucket.
So the rotating bucket points to a deeper, invisible layer of motion happening in absolute space. This seemingly simple experiment throws a wrench into the idea that all motion is relative.
Precisely. It suggests that there's more to motion than meets the eye, a hidden framework guiding those forces we observe.
Oh, okay.
And to illustrate this further, Newton presents another thought experiment, this one involving two globes revolving around each other in the vast emptiness of space.
Okay. Two globes in empty space. I'm already intrigued. Tell me more.
All right, so imagine two globes connected by a cord,
Okay.
evolving around their common center of gravity,
Gotcha.
even in the absence of any other objects.
Right.
Even in the void.
Yeah.
Newton argues we could tell if they were truly rotating based on the tension in the cord.
So even if the globes are the only things that exist,
Yeah.
even if there's nothing else to measure their movement against,
Yes.
the tension in that cord would reveal their true motion, their rotation within absolute space.
Exactly. The cord becomes a witness, a tangible indicator of a motion that's happening on a deeper level,
Ah.
relative to absolute space. And the amount of tension in the cord would change if you applied a force to the globes, further demonstrating the link between force and true motion.
It's like absolute space is this invisible hand orchestrating the dance of the cosmos.
Yes.
And we can catch glimpses of its influence through these forces and their effects on objects.
That's a beautiful way to put it. For Newton, the existence of absolute space wasn't just some abstract philosophical notion.
Yeah.
It was a necessary consequence of his observations of the physical world and his deep-seated belief in the mathematical order of the universe.
Okay, so Newton has laid out his arguments, his defense for this invisible framework that governs the cosmos.
Yes.
But I know he wasn't the only one pondering these profound questions.
Right.
Thinkers like Leibniz and Berkeley had some serious issues with his ideas, didn't they?
Oh, absolutely. They weren't afraid to challenge Newton's framework.
Yeah.
And their critiques get right to the heart of some of the biggest philosophical questions about the nature of reality and how we know what we know.
Well, I'm ready to hear those critiques. Let's dive into the alternative views and see how they stack up against Newton's grand vision. All right, we've journeyed deep into Newton's mind, explored his arguments for absolute space and time.
Yes.
It's a powerful framework.
Yeah.
But, as we hinted, not everyone was on board with his ideas.
Right.
Thinkers like Leibniz and Berkeley had some strong critiques.
They did.
And for a philosopher like you, this is where it gets really juicy.
Absolutely. These critiques get to the core of how we understand reality knowledge and the role of science. Let's start with Leibniz.
Okay.
He was a staunch advocate for relational space, meaning he believed that space is defined by the relationships between objects,
Okay.
not as something that exists independently.
Right.
He'd argue that it's more meaningful to talk about distances and positions of objects relative to each other, not to some absolute invisible grid.
So for Leibniz, the universe is less like a stage with fixed coordinates
Yes.
and more like a giant web of interconnected relationships.
Exactly. He'd say, why invent this concept of absolute space if we can explain everything we observe through the relationships between objects?
Yeah.
It adds unnecessary complexity.
Right.
Think about those revolving globes Newton used in his thought experiment.
Oh, okay.
Leibniz would argue that the tension in the cord is a result of the relationship between the globes, not their motion in absolute space.
That's a really interesting point. It shifts the focus from this grand external framework
Yes.
to the interactions happening within the system itself.
Right.
It's almost like a more grounded, pragmatic approach to understanding motion.
It is.
And what about Berkeley?
Yes.
Didn't he take things even further?
He did. Berkeley was an empiricist, meaning he believed that knowledge comes primarily from sensory experience.
Right.
He argued that the very idea of absolute space is nonsensical because it's something we can't perceive. He'd say if we can't see it, touch it, smell it, hear it, or taste it,
Right.
how can we even claim it exists?
So for Berkeley, absolute space falls outside the realm of what we can know.
Yeah.
Because it's beyond the reach of our senses.
That's right.
It's like he's drawing a line in the sand saying science can only deal with what we can observe directly,
Yes.
not with these abstract, invisible entities.
Exactly. He was deeply skeptical of any concept that couldn't be grounded in sensory experience.
Mm-hmm.
And, in many ways, Berkeley's critique foreshadows some of the challenges modern physics has posed to our understanding of reality.
Yeah.
Think about quantum mechanics,
Right.
with its particles that can be in multiple states at once,
Yeah.
or its entanglement where particles seem to communicate instantaneously across vast distances.
Right.
These are phenomena that defy our everyday intuitions about space and time.
It's mind-blowing.
Yeah.
So these critiques from Leibniz and Berkeley, while they arose in the context of Newtonian physics,
Yes.
they still resonate with some of the most perplexing questions we face in modern science.
They do.
It's like they were ahead of their time.
They were, and that's what makes studying the history of science and philosophy so fascinating. You see how these ideas evolve, how they challenge and refine each other across centuries. And for a philosopher,
Yeah.
these debates highlight the limitations of human knowledge,
Right.
the challenges of defining reality,
Yeah.
and the ongoing dialogue between our observations and our conceptual frameworks.
It really makes you appreciate how much our understanding of the universe has evolved since Newton's time.
It does.
But it also makes you wonder, if Newton were alive today, how would he react to modern physics,
Right.
with its theories of relativity and the mind-bending world of quantum mechanics?
That's a question that could fuel a whole other deep dive.
Right.
It's impossible to know for sure,
Yeah.
but knowing Newton's brilliance and his deep commitment to uncovering the mathematical laws of the universe,
Right.
I imagine he'd be both intrigued and challenged.
I can picture him poring over Einstein's equations,
Yes.
wrestling with the idea of space-time,
Yeah.
a concept that unites space and time into a single dynamic entity.
That's right.
And perhaps he'd even find a way to reconcile his absolute framework with these new ideas,
Possibly.
seeing relativity as a refinement or extension of his original vision.
Right.
Or maybe he'd be a staunch critic of quantum mechanics,
Yeah.
resisting the idea of an inherently uncertain universe.
Yeah, that's possible too.
It's tantalizing to think about. But, regardless of how he might have reacted,
Yeah.
one thing's for sure.
It's that.
Newton's legacy extends far beyond his specific theories.
It does.
He sparked a revolution in scientific thought,
Absolutely.
pushing us to think more deeply about the nature of space-time motion and the very fabric of reality.
Couldn't agree more.
And for a philosopher, his work serves as a constant reminder to question our assumptions, explore alternative viewpoints, and push the boundaries of what we think we know.
Well said.
So as we wrap up this deep dive into Newton's universe, I think we've left our listeners with plenty to ponder.
I think so too.
The debate about the nature of space and time is far from settled.
Right.
And as we grapple with the mysteries of the cosmos, both on a grand scale and in the subatomic realm,
Yeah.
those fundamental questions about reality and perception remain as relevant as ever.
Absolutely. It's a testament to the enduring power of these ideas and the ongoing quest to understand our place in this vast, awe-inspiring universe.
And on that note, we'll leave you to contemplate those big questions. Thanks for joining us on this deep dive into the mind of Isaac Newton. Until next time, keep questioning, keep exploring, and keep diving deep.